Okay, so remember to record. I'll try to make a recording available to you after each session, in case you missed anything here. All right, so the first thing that we are going to look at here is maybe multiplying a couple polynomials together. And in particular, we will look at how to multiply a couple of binomials together here. So we're going to multiply two binomials together. Binomials are two-term polynomials. Terms are always separated by additions or subtractions. Now, there's a million ways to show how to multiply binomials together. Probably the more orthodox way, it is demonstrated in most textbooks, is the FOIL method. Okay, FOIL is an acronym that stands for first, outer, inner, and last. So basically, when we multiply binomials together, we multiply the first terms together. And of course, you got to keep in mind rules of exponents, that when you multiply like bases together, you keep the base the same and you add the exponents. You're going to need to know that. So when you take 4x times 2x, all right, plus, and then you're going to have to multiply the outer terms together, 4x times 10, plus, and then you multiply the inner terms together, negative 5 times 2x. And then you cannot forget to wrap this up by multiplying your last terms together. Negative 5 and 10 get multiplied together. All right, so this is the product of the first terms of the binomials. This represents the product of the outer terms, the product of the inner terms, and the product of the last terms. Hence, you get that word FOIL there, okay? All right, so 4x times 2x is going to net us 8. Now, x to the first power times x to the first power is x to the second power. So 4x times 2x is 8x squared. Plus 4x times 10 is 40x. Negative 5 times 2x is minus 10x. And negative 5 times 10 is minus 50. The two middle like terms need to be combined, and hence the product of these two binomials is going to net us this trinomial of 8x squared plus 30x minus 50. Okay. And notice that our product, this trinomial, is written in descending order as the degree of each term decreases from left to right. Second degree term, first degree term, and then 0th degree term there. Any questions how I multiplied these two binomials together there? All right. And in all reality, ladies and gentlemen, if you've never done that before ever in your life, multiply two binomials together like this, I mean, or in general, college algebra is not the class to be starting with. Okay, you should be starting with elementary algebra. All right, so we just demonstrated how to multiply these binomials out here, and hopefully this is a review, and it should be review, being college algebra here. Any questions about that there? Any questions? All right, so notice when you take a two-term polynomial and multiply it by a two-term polynomial, you generate four products, four arrows, four products, 1, 2, 3, 4. That's always going to be the case. When you take an m-term polynomial and multiply it by an n-term polynomial, you're always going to have m times n products. All right, any questions about this here? All right, well, let's take this, let's try to multiply a binomial by a trinomial. So let's try to take 6x minus 4. Let's see if we can multiply this by 2x squared minus 3x plus 15. So I'm going to multiply a binomial by a trinomial, and since I'm multiplying a two-term polynomial by a three-term polynomial, I would expect to get 2 times 3 or 6 products, or 6 arrows when we get done. I would recommend that you use the arrows as a visual cue. Now, we don't have any nifty name like FOIL for this situation like this. We just got to make sure that each term of the first polynomial gets multiplied by each term of the second polynomial. So 6x is going to get multiplied by 2x squared. Plus 6x will get multiplied by the negative 3x. Plus 6x gets multiplied by the constant term at the end here, this 15. All right, now we're done with the 6x. We move to the minus the negative 4 here. Negative 4 gets multiplied by 2x squared. Plus negative 4 gets multiplied by negative 3x. Plus, finally, negative 4 gets multiplied by 15 at the end. All right, and notice we have 6 arrows, as mentioned, and we have 6 products here, okay? So 6x times 2x squared is going to be 12x cubed. 6x multiplied by negative 3x is minus 18x squared. 6x multiplied by 15 is going to be 90x. Negative 4 times 2x squared is minus 8x squared. Negative 4 times negative 3x is plus 12x. Negative 4 times 15 is minus 60 at the end. We should always try to combine like terms. Notice this third degree term does not have anything to combine with, so we just bring it on down. We normally like our answers to be in descending order also, so the degree of each term should decrease from left to right. That's usually customary in mathematics to do so. I mean, it's not a mistake if you don't have it in descending order, but like I said, we normally try to do that. Negative 18x squared minus 8x squared. Negative 18 minus 8 is minus 26, so we got minus 26x squared. So therefore, our quadratic terms combine to give you negative 26x squared. Our linear terms, our first degree terms combine, 90x plus 12x, combined to give us 102x. And last but not least, we have the constant term of minus 60 at the end. That has nothing to combine with. And so this would be your simplified product of this binomial and that trinomial. Any questions how we multiplied the binomial and trinomial together there? This is your answer right here. And notice it is written in descending order as the degree of each term decreases from left to right here. Okay. All right, any questions here so far? All right. Okay, maybe you can try one here. We'll call this classwork number 1. Today's date is September 12th. Put this at the top of your paper and also your name. And I would like you to email these classworks to me always by midnight of the day they're issued. So just make sure I get this classwork to me by midnight tonight, and you'll get paid for the day. All right, I would like you to try to multiply these polynomials together and just make sure your final answer is simplified. All right, so take this binomial here, 2c squared plus 3c, and see if you can multiply it by this trinomial. Okay. All right, so we're going to multiply 2c squared plus 3c by this trinomial here. Go ahead and do that, and we'll check your work, okay? All right, so we'll call that classwork number 1 there. The square root of 25 is just 5, so it's going to be 6 times 5. Plus here we got 3 square root of 5 times 4 square root of 2. 3 times 4 is going to be 12. And the square root of 5 times the square root of 2 is going to be the square root of 10. Square root of 10 cannot be simplified. There's no perfect squares. Whoops, there's no perfect squares underneath here. And finally, 3 square root of 5 times 1 is just 3 square root of 5. All right, so we have 6 times 5 is 30, plus 12 times the square root of 10, plus 3 times the square root of 5. And notice there's no like radicals that need to be combined in here. None of these square roots can be further simplified as there are no perfect squares underneath them. So this would be it. That would be your simplified product of this 1 term and times the 3-term radical expression there. All right. Any questions on this page here? Okay. Now we'll try to multiply two-term radical expressions together. 4 times the square root of t plus 10. Multiply that by 3 square root of t minus 8. Unfortunately, these are not conjugates of each other. And because of that, we're going to have to multiply it all out. So we multiply our first terms together. So we got 4 square root of t times 3 square root of t. And 4 times 3 is 12. The square root of t times the square root of t is the square root of t squared. But the square root of t squared is what?
Just t.
T. So 4 square root of t times 3 square root of t is 12t. Then we're going to multiply the 4 square root of t times the negative 8 way over here. So 4 times a negative 8 is minus 32. And you got to attach the factor of square root of t. Multiplying the inner terms together, we got 10 times 3 square root of t. 10 times 3 is plus 30. And you're going to attach the square root of t. Finally, the last terms, 10 times negative 8 is minus 80. Are there any like terms or like radicals that need to be combined in here? These are like radicals, correct? They need to be combined. They're both square roots of t. So please don't leave your answer looking this way. You will be expected to combine these. So negative 32 square root of t plus 30 square root of t is going to net us negative 2 square root of t minus 80. And that would be it. That's all you can do with this. There's nothing else to simplify or combine. Okay. Any questions how we multiplied that radicals out there like that? Kind of using our FOIL algorithm, agree? Kind of like using our FOIL algorithm. All right, now we got 3 square root of 7 minus square root of 5. And this will get multiplied by 3 square root of 7 plus the square root of 5. Why is this going to be an easy one to do?
They are conjugates.
All right, because these are conjugates of each other. To multiply these out should be pretty simple. We do not have to FOIL it all out. The two middle terms will always drop out in such a situation whenever you're taking the product of conjugates. All we got to do is just square our first term, square our last term, and place a minus sign in between them, and that's it. That would be the product. Now, when you square the 3 square root of 7, 3 squared is 9, and times the square root of 7 squared is just going to be 7. So it'd be 9 times 7 minus. When you square the square root of 5, that'll be the square root of 25, which is just 5. And so we're going to have 63 minus 5, which is going to be 58. And that is it. That would be the product of those conjugates there. All right, any questions about how I'm multiplying this stuff out here? I multiply those out there.
I have a question.
All right, go ahead.
So when you squared the square root of 7 and the square root of 5, so they respectively came 49 and 25.
Yeah, when you square the square root of 7, it's the square root of 7 times the square root of 7, which is the square root of 49. But the square root of 49 is just what rational number? 7, correct?
Yeah.
And likewise, when you square the square root of 5, it becomes the square root of 5 times the square root of 5, which is the square root of 25, which is just 5. The bottom line is this, shortcut. When you square a square root, the square root and the square disappear. And the result is what's underneath the square root, correct? That's all there is to it. All right. That's true with any root. If you have an nth root of a and you raise this to the nth power, your result's going to be a. True?
Yep.
Always true. Okay. All right. Any other questions about this here? Okay, I'll give you classwork number, what is it? Number 2, I believe, correct?
Yeah, we're on 2.
All right, here we go. Number 1, I want you to multiply this out here. So 4u squared minus 5v squared Multiply that by 2u squared plus 3v squared. Number 2, see if you can multiply 3y plus 6 by 1/3 y squared minus 5y minus 4. And multiply a couple radical expressions together. 3 square root of 11 minus 7 square root of 2 multiplied by 2 square root of 11 plus 9 square root of 2. And the last one, see if you can multiply this out here, the square root of x plus y minus the square root of x minus y quantity squared. Okay. All right, so we'll call that classwork number 2. See if we can work those out. Got that? All right, number 1.
Yep, I got it.
Yeah.
All right. Number 2, multiply this all out. And we get all those products there, and you do have a fraction here, but 3 times 1/3 is just 1. And then you will ultimately, and you got 6 times 1/3 is 2. And right there. So then you gather together your like terms, put this in descending order, and you get this y cubed 3rd degree polynomial. Do anybody get this here? This product?
Yeah.
Yeah.
All right, so
Yeah.
we're doing okay in general out there so far?
Wait. Let me see if I'm looking at this correctly. Okay, yeah. I can see the bottom part of it. I couldn't see the 3rd line. We're good.
Okay. We got that there. And number 3, we're multiplying some radical expressions together, and unfortunately, they're not conjugates of each other. So number 3, we're going to have no choice but to multiply it out the long way and multiply it all out. 4 products, kind of using the FOIL algorithm to multiply it all out. And notice a lot of these square roots disappear because you end up taking the square roots of perfect squares here. 2 middle radicals turn out to be like radicals, and they need to be combined here. And did anybody get that final result there on that one?
Yes, but I have a question.
Mm-hmm.
Does it matter what order we have them in? Because I have 13 root 22 minus 60.
No, that doesn't matter here.
Okay.
There's really no such thing as descending order in a situation like this. All right. So that's problems 1 through 3. Does it look like in general we got those? Now this is being recorded, so if you did miss this, you can always go back and look at the recording here. All right, the last one, we're basically squaring a radical expression. And they are, when you square 2-term expression, you can always tap into what we got here is we got a minus b squared. But nonetheless, you can tap into this pattern here, which is going to be a squared minus 2ab plus b squared. All right. Instead of multiplying it all out, so all you got to do is square your first term minus 2 times the first term times the last term plus the last term squared. You see that there? Actually, the last term would be is always going to be a positive here. So when you square a square root, the square root and the square disappear. So x plus y drops out from underneath here. Likewise, x minus y is the result of squaring the square root of x minus y. And then when you multiply the inner radicals together, you get the square root of x plus y times x minus y. And these are conjugates of each other, x plus y and x minus y. So their product would give you x squared minus y squared. Finally, the x's combined, x plus x gives you 2x, and the y's drop out. Y minus this y takes the y's out of the picture, and that'd be your final result. Anybody get that? Okay. All right, Anastasius. Stasia says, yes, I got that. Okay. All right, so there we have it, ladies and gentlemen. That section now is in the archives. We did a couple of polynomial operations in that section. And also we transferred the algorithms from polynomials to radical expressions as far as multiplying is concerned. Okay. All right, one last section today is R5, and that's going to have us turn our attention to factoring polynomials. And I will attach what's called a factoring toolbox on our Canvas course site for your use. There's all different types of polynomials to factor. Normally, the first type of factoring you do with polynomials in elementary algebra is you first of all try to factor out a greatest common factor, okay, out of terms. So greatest common factor. So let's take a look here. Suppose I have like 12x squared y, this monomial versus let's say 16x y, let's say y cubed. I'm going to make this also x cubed here. Okay, so what would be the greatest common factor or greatest common divisor of both these monomials? Well, as far as the coefficients are concerned, 12 and 16, what is the largest number that divides into 12 and 16? The greatest number you can think of that divides into 12 and 16.
4.
All right, so 4 looks like it would be the greatest or the biggest number that divides evenly into 12 and 16. So the greatest common factor would have us having a factor of 4 in it. As far as the variables are concerned, it's somewhat of a paradox, but when we're finding the greatest common factor, you always take the least exponent out when it comes to variables. Least exponent. Now, if this was a least common multiple, we would take the greatest exponent, but greatest common factor, take the least exponent. I know it sounds a little weird, but as far as our GCF is concerned, we would only have to we would only be able to use how many factors of x? 2 of them or 3 of them? Well, the least exponent between 2 and 3 is 2, so we can only have x squared appearing in our greatest common factor. As far as y is concerned, we only have 1 factor of y appearing here, but 3 factors of y here. The least exponent of 1 or 3 y's is 1y, so we can only have 1 y in our greatest common factor. This would be your greatest common factor of both of these monomials, 4x squared y. That makes sense here? This is the largest or greatest expression that divides into both this monomial and this monomial evenly. So just remember, when it comes to the variables, you always choose the smallest exponent, the least exponent, when determining how many of those to include in your greatest common factor. All right, so now that we have a little idea as to how to find greatest common factors of monomials, we can then use that to begin to factor polynomials now in general. So let's see if we can embark on that. So our instructions change from simplify or multiply to factor. And so we will just dive right in and try to start factoring some polynomials here. Now, to factor a polynomial means to rewrite the polynomial as the product of polynomials. So if we want to factor this trinomial here, first of all, we would probably want to identify what the greatest common factor is for all 3 of these terms. Let's just look at the numbers, 15, 30, and 5. What's the greatest common divisor or factor of 15, 30, and 5?
5.
5.
So we can definitely factor a 5 out of all 3 terms. How many factors of C can I factor out of all 3 terms? 3 of them, 4 of them, or 5 of them?
3.
Yeah, when it comes to the greatest common factor, you can only factor the least exponent out. So I can only factor C cubed out of all 3 terms. The reason why that is because, like, if you try to factor C to the 5th power out of all 3 terms, C to the 5th would divide into this term evenly, but it would not divide into C to the 4th and C cubed. That's why you must factor only C cubed out of each of the 3 terms, because C cubed will divide into C cubed, C to the 4th, and C to the 5th. Now, when I divide out or factor out 5C cubed, what do I leave behind inside my parentheses? as a factor, you could ask yourself, what do you have to multiply 5c cubed by to give you 15c to the fifth?
3c squared.
3c squared, exactly. You got a minus sign. 5c cubed times what? It gives me back 30c to the fourth. That'll be 6 what? 6c, correct? Gives you back 30c to the fourth. Finally, what do you multiply 5c cubed by to give you back 5c cubed? Well, that would be 1. And there you go, ladies and gentlemen. We have factored this trinomial here, this 3-term polynomial, into the product of a monomial and a trinomial. Okay. You know, this trinomial cannot be further factored down. In passing, we'll just say that. All right, let's try another one here. What if I have 4t times u plus 8v minus 3 times u plus 8v? This is a strange looking polynomial, but upon further inspection, you can hopefully see that between this term here and this term here, both these terms share a common factor. And what would be that common shared factor? It would be the binomial u plus 8v. You agree that's shared between both these terms here. Being the case, I can factor the whole binomial factor of u plus 8v out of both terms. There it is. Times, what would I leave behind in doing that? Well, when you factor the u plus 8v out of the first term, think of it as having been crossed out because it's out here. You leave behind 4t. And when you factor out u plus 8v out of the last term, you leave behind minus 3. And there we go, ladies and gentlemen. This would be the factorization of that polynomial. There's a case where we factored out a common binomial factor, correct? You ever remember having done that before? All right, 6ty plus 9y plus 14t plus 21. We want to try to factor this 4-term polynomial here. And whenever you're factoring a polynomial, your initial question should always be, can I factor anything out of all the terms of the polynomial? Like back with this one, we were able to factor out 5c cubed out of each of the 3 terms. That's why we did so. All right, so as we stare at all 4 of these terms here, can we, other than 1 or -1, factor anything out of all 4 of these terms?
No.
The answer is no. So the greatest common factor of all 4 of these terms happens to be 1 or -1. By the way, you can always factor 1 or -1 out of any polynomial. Those are called the trivial factors. But other than 1 or -1, there is nothing we can factor out of all 4 terms here. So to factor this, we're going to have to try to use a different technique. And that different technique is called the grouping method. So in other words, when we have a 4-term polynomial, we usually are finding success in factoring it using this technique called the grouping method. Okay. Now the grouping method, as it suggests, is going to have us using grouping symbols. And so I'm going to throw parentheses around my first and last 2 terms to literally group them together. And now we're going to put the spotlight on the first 2 terms and ask ourselves, what can I factor out of the first 2 terms, 6ty and 9y? So what's the greatest common divisor of both these terms here?
3y.
Okay, so we can factor a 3y out, times what would I leave behind in factoring 3y out of 6ty? 3y times what gives you back 6ty?
2t.
2t plus 3y times what would give you back 9y? Plus 3. Okay, plus now shift our focus to the last 2 terms. What can we factor out of 14t and 21? What's the greatest common divisor of both these terms?
7.
7. That's it. Notice you cannot factor a t out of the last 2 terms because the last term does not have a factor of t. All we can do is factor a 7 out. When I factor the 7 out of 14t, I leave behind 2t. And when I factor 7 out of 21, I leave behind 3. Now, ladies and gentlemen, notice we do have a common binomial factor of 2t plus 3 that itself needs to be further factored out of both these terms. So we will now factor out the 2t plus 3 out of both these terms. There it is, times what do I leave behind? I will leave behind 3y plus 7. And we are done. This is the factorization of this 4-term polynomial. That's called the grouping method. Does that ring a bell? Have you ever done it before? The
Yes.
grouping technique.
Yeah.
Okay. And if you were to multiply this back out, and gather together any like terms, you would get back what you started with. And you should, or else you made a mistake somewhere. So a way of checking your factorization is to remultiply your polynomials back together and see if you get back what you started with. If you do, you have the correct factorization. If you don't, there's something wrong. Okay. All right. So that's how we factor a 4-termer. We tend to use this grouping method. Now, grouping doesn't always work. Sometimes polynomials are not factorable, or they are prime, as the case might be in rare circumstances, but that was definitely a factorable one there. All right, maybe we could try another 4-termer here. CD, try to factor CD minus 8D plus 4C minus 2D squared. We will try to factor this 4-term polynomial. And as we look at each of these 4 terms, we ask ourselves, can we factor anything out of all 4 terms except 1 or -1? And the answer is, it don't look very good. Do you agree? Can't factor a D out of all 4 terms because the 3rd term does not have a factor of D. So doesn't look like there's anything we can do to factor this. Well, because it's a 4-term polynomial, we will try to employ the grouping method. So we'll throw parentheses around our first 2 terms and our last 2 terms in hopes of having the grouping method factor this. Now, what can I factor out of the first 2 terms? I can factor out a D, and that would leave behind C minus 8. The last 2 terms, I can factor out just a 2, and that leaves behind 2C minus D squared. Well, this don't look good at all because we don't leave behind the common binomial factor. So something's wrong. It doesn't look like the grouping method is working on this 4-term polynomial. This is not getting us anywhere. Okay. Well, as sometimes with a polynomial, you may have to rearrange your terms a little bit to force it into a polynomial that is indeed factorable. So what I'm going to do is take my 4-term polynomial here, and I'm going to flip these 2 middle terms. I'm going to interchange these 2 middle terms here. So I'm going to rewrite my 4-term polynomial as CD plus 4C minus 8D minus 2D squared. Now we might have better luck in factoring this equivalent 4-term polynomial utilizing the grouping method. So I put parentheses around my first 2 terms. Now, when you have a 4-term polynomial and you're using the grouping method, whenever you have a minus sign that precedes your 3rd term, you got to try to remember something. I leave the minus sign outside the parentheses, but if you do that, you just have to try to remember to change the sign of your last term to avoid a sign mistake. So this minus 2D squared has to become a positive 2D squared. So you have to have a little bit of a sign adjustment when you have a minus sign in front of your 3rd term of a 4-term polynomial. Okay. All right, what can I factor out of the first 2 terms? I can factor out a C, leaving behind D plus 4. Last 2 terms, I can factor out a 2 and a what? D, leaving behind what? Well, let's see here. Leaving behind what? 4 plus D. But do you agree that D plus 4 is equivalent to 4 plus D? Isn't that true?
Yes.
Now we're lucky because we have left behind the common binomial factor of D plus 4, of which can now be factored out of both these terms. Hence, I'll factor the D plus 4 out, times, what do I leave behind after doing that? I'll leave behind C minus 2D. And ladies and gentlemen, this is the correct factorization of this 4-term polynomial. So there might be times when you may have to rearrange some terms in your polynomial to force it to be a factorable polynomial, okay? And that's a classic example there where we had to flip around these 2 middle terms here to enable the grouping method to work. So try to, remember that, as your author is always playing tricks on you at the end of your sections in your textbook. There's times when you have to actually manipulate your polynomials a little bit before they're rendered factorable. Okay. All right. Let's see here. All right, then we get into the trinomial family. Factoring trinomials. The first type I would like to show you are the ones that possess a leading coefficient of 1. These are called the easy types of trinomials to factor. All you need are a couple of factors of the constant term that sum up to your middle coefficient. So back in early algebra, sometimes they call this the product sum method for factoring these types of trinomials. And there's other ways you can show this, but this is a very common method. We need our product to be the constant term of plus c, and we need the sum to be the middle coefficient of plus b here. So if I can find a couple of factors of c, maybe like c1 and c2, such that those factors add up to give me my middle coefficient, then I can factor this trinomial immediately into the product of two binomials, of which would be x plus c1 times x plus c2. And this would be the factorization of that trinomial. Do you remember having seen that method before? For these type of trinomials?
Yes.
Okay. Product sum method. Okay, so let's see if we can factor a couple of these here. How about w squared plus 5w minus 66? We want to try to factor this trinomial. Another thing I want to point out that's very important. Normally, we wave our hands at this in early and intermediate algebra, but we say that this trinomial is quadratic in form. It's a quadratic form trinomial, in the sense that the degree of the leading term is twice the degree of the middle term. And any polynomial or trinomial that has this structure where the leading term is of degree twice the degree of the middle term is said to be a quadratic form trinomial. And it's only these quadratic form trinomials that do factor into the product of two binomials. If it's not quadratic in form, then it's not eligible to be factored like this. For instance, if this was like x cubed and this is x, we're out of luck because it would not be a factorable quadratic form trinomial. But if it's like x squared and this is x, and this is a constant term, or if this is x to the 4th power and this is x to the 2nd power, and that's a constant, that's a quadratic form trinomial. It would factor into the product of two binomials in the situation that two factors of the constant term add up to the middle coefficient. All right, so here we go. We're going to try to factor this easy type of trinomial. It's an easy type because the leading coefficient is 1. All I need are a couple of factors of negative 66, or I need two numbers that give me a product of negative 66. And they also have to then give me a sum of my middle coefficient of positive 5. So can you think of a couple of factors of negative 66 that add up to 5? And you may have to, comprise a list here, and your calculator will help you build that list. So like negative 1 and 66, negative 2 and 33, negative 3 and 22, 4 don't go into 66 evenly, 5 doesn't, 6 does, negative 6 and 11, 7 don't divide into 66, 8 doesn't, 9 doesn't, 10 doesn't, 11 does, and we're done. Can you find a couple in this list that sum up to 5? Couple of factors in this list that add up to 5 or middle coefficient.
6 and 11.
These are the only ones that work. These are the only factors of negative 66 that do indeed add up to our middle coefficient of positive 5. Therefore, this trinomial factors immediately into two binomials, of which would be w minus 6 times w plus 11. And we're done. That would be the factorization of that trinomial. Or you could have these switched. You could have the w plus 11 here times the w minus 6. You remember factoring those types of trinomials, the easy types?
I remember doing so in a diamond, sort of like an X
Yeah,
formation.
there's many other ways, to show the factorization of these trinomials. I've seen the diamond method. I don't really use it. I actually forgot how it works. But hey, look, if you got another way of factoring a trinomial like this, other than my product sum method, if you can show the work and get the correct answer, don't worry about it. You're just as accurate as anybody else, okay? All right, because I do realize there's many ways of showing how to factor these types of trinomials, and there's a couple of different ways of factoring the difficult ones, of which I'm going to embark upon next. But does this make sense how we factor this easy type of trinomial here? One with a leading coefficient of 1. All you have to do is find 2 factors of the constant term that add up to the middle coefficient. Once you find them, you can immediately then factor your trinomial using your choice of decided upon factors and to factor your trinomial. All right. Now, if I had like t squared plus 5t plus 7, all right, and I wanted to try to factor this trinomial, do there exist 2 factors of 7 that add up to 5? And normally, when we get good at factoring these easy types of trinomials, we don't actually build this formal table over here. It takes too much time. We normally just search for a couple of factors of 7 that add up to 5, and factors of 7 would be 1 and 7 and -1 and -7. Do you agree? But none of these add up to +5. So therefore, we would say that this trinomial here is non-factorable. Or some authors call these types of polynomials that cannot be factored, they call them prime polynomials. Okay, so if a polynomial is a prime polynomial, that means it cannot be factored. And so that's a non-factorable prime trinomial, correct? Does not factor. You might run into these from time to time. Once in a while, maybe I'll slip one of those in on your quiz or your exam. You never know, so be on guard for those. Just for the record, I'll never give you a quiz or exam where everyone is non-factorable. So don't use this as a cop-out or take this lightly. If it's non-factorable, you write non-factorable, it better be non-factorable, agree? All right. All right, those are the easy types of trinomials to factor when the leading coefficient is 1. But what if the leading coefficient is not 1? Well, then the trinomials are more difficult to factor. So for instance, if I have 2c squared, let's see here, trying to cook one up here. Okay, so let's say like -6 is the constant at the end there, and I got -c here. All right, so how would I factor this trinomial here? This is no longer an easy type of trinomial to factor because the leading coefficient is no longer a +1. These are the more difficult types of trinomials to factor. Notice my middle coefficient is understood to be a -1. Notice there's nothing we can factor out of all 3 terms here. And so how would we factor this trinomial? Well, ladies and gentlemen, there's 2 main methods. There's a trial and error method for factoring these types of trinomials, and there's what's called the grouping technique or the grouping method. Those are the 2 most common methods that are portrayed in textbooks. And you may have some other method that works for you. If it works, there's no problem. You can use that. All right. The trial and error method, like I said, is kind of like a common method. What we do here with the trial and error method is we take our first term, which is like 2c squared, and we take our constant term, which is -6 there, and we try to find a combination of factors between the first term and the last term that multiply and add together in such a way so as to give us our middle term of -1c. So some trial factors for 2c squared would be 1c times 2c. Trial factors for -6 could be -1 and 6, or 1 and -6, or -2 and 3, or 2 and -3. All right. So here comes the trial and error portion of this problem, trying to come up with a combination of factors between this first column and the second column that multiply together and add up to give us a -1c. For instance, you could have one trial go like this. You could say 1c times -1 plus 2c times 6. So 1c times -1 plus 2c times 6. What do these multiply and add up to give us? That's going to be -c plus 12c, but these add up to 11c, and that's not going to work because they must sum up to -1c. So this combination is not going to work. You could try maybe like 1c and -2 plus 2c and 3. Try this combination here. This is going to give you negative 2c plus 6c, which adds up to 4c. But unfortunately, they still don't add up to a negative 1c. So this is, you know, a trial and error thing here between these two columns to come up with the right combination that works. If you find it, then you can immediately factor your trinomial. So can anybody between this list and this list here find a combination of factors that will multiply together and add up to give you negative 1c? You know, if I take 1c times negative 3, and then I add to that 2c times 2, this is going to afford me negative 3c plus 4c, which adds up to 1c. Do you agree? I'm getting closer, but I still need a negative 1c for the sum. Well, we can arrange for that. Just flip these signs around. How about a negative 2 and a positive 3, which are still factors of negative 6? What if I take 1c times a positive 3 plus 2c times a negative 2? That's going to give me 3c minus 4c, which finally add together to give me 1c. Okay, whoops, 1c. So as it turns out, this looks like the combination that's going to work. 1c times 3 plus 2c times negative 2. Therefore, this trinomial will factor immediately. I'll put the 1c here and maybe the 2c here. The 1c had to get multiplied by the 3, so the plus 3 has to go here to afford that to happen. And the 2c has to get multiplied by the negative 2, so the minus 2 has to go here to afford that to happen. And that would be your factorization. So that's called the trial and error method, ladies and gentlemen. And if you're into that, you love it, more power to you. Go with it, use it, and hopefully we get the correct factorization. Another technique that I always intend to lean towards a little bit more so, especially in the early courses in algebra, is the grouping method, because it minimizes the amount of trial and error. When these two lists here get long, now fortunately this was a short list here, but sometimes this list is long and this list is long, and then you're having to try a lot of different combinations between the two lists to try to get that middle term, and that can burn a lot of time. So there is another little more systematic method for factoring these difficult trinomials called the grouping method. If you've never seen it before, who knows? Maybe you'll fall in love with it right here and now. But to initiate this grouping technique, we start by taking the product of the leading coefficient and the constant term. So I'm going to take 2 times negative 6 here. That gives me negative 12. And then I need two factors of negative 12 that add up to give me negative 1, the middle coefficient. This is where the only trial and error portion of this method comes into play, right here. Once we find these factors that sum up to negative 1, the rest is all systematic. That's why I like this method better, because you don't have all this guessing to do between these two columns. Okay, can you think of a couple of factors of negative 12 that add up to negative 1, the middle coefficient? After a little thought, hopefully you'll stumble across negative 4 and 3 as being factors of negative 12 that do indeed add up to what we need, namely negative 1, correct? So now that we found our factors that are going to work, negative 4 and 3, we're going to rewrite this trinomial as an equivalent 4-term polynomial, where the middle term, this negative 1c, is going to be split up and written as the sum of our decided upon factors over here. So I'm going to rewrite this 4-termer as 2c squared plus 3c minus 4c plus 3c minus 4c minus the 6. Or look, you could have these switched around. You could have the minus 4c and then the plus 3c. Doesn't matter. You'll get the same factorization. I chose this to illustrate something. Ladies and gentlemen, I got a 4-term polynomial. So how do I factor 4-termers? I use what technique? Grouping, correct? Notice I have a minus sign that precedes my third term. Be careful how you group your last two terms together. Just make sure you change the sign of your last term to avoid a sign error. I always like to leave my minus sign outside the parentheses, in which case I must change the sign of my last term. First two terms I can factor out a c, leaving behind 2c plus 3. Last two terms I can factor out a 2, leaving behind 2c plus 3. We now got that common binomial factor of 2c plus 3 that can be factored out, times what would I leave behind? C minus 2. And that difficult trinomial has been factored. This is called the grouping method. You agree I got the same factorization? Same factorization, correct? No, the factors are in a different order, but it don't matter. It's still the same. So whether you use the trial and error method or the grouping method, take your pick. The trial and error method has pros and cons, just like any other technique. The good thing about the trial and error method is once you find the combination that works, boom, you can directly factor your trinomial. The bad thing is you might have a hard time trying to find the correct combination, especially when these lists get long. The grouping method, the bad thing about the grouping method is there's a lot of steps. The nice thing about the grouping method is there's only a little bit of trial and error back over here. Once you find the combination of factors of the product of the leading coefficient and the constant term to sum up the middle coefficient, then the rest is all just mechanics, just using the grouping method. Okay, so there's goods and bads with both techniques. You basically have to find a technique that you're comfortable with and get good at it and use it. Okay. All right. So, okay. All right. So now the next thing that we run into is the binomial family. Binomials. We have what is called the sum of squares. And the sum of perfect squares is always non-factorable. You cannot factor the sum of squares over real numbers. You got the difference between squares, and the difference between squares can be factored, and it can factor into the product of conjugate binomials. You recognize it? That's how the difference between perfect squares always factors. And then you got the sum and difference of perfect cubes. So when you have the difference between perfect cubes, it can factor, and it would factor according to this pattern here. Okay, so that's how the difference between these perfect cubes factors into the product of the binomial and the trinomial. And then you got the sum of perfect cubes. The sum of perfect cubes factors in a similar way as a product of a binomial and a trinomial. An easy way to remember all these signs in here is to use this acronym called SOAP. I don't know if you've ever seen this before. Same, opposite, always positive. Okay, so the signs are always the same between this sign and this sign. The signs are always opposite. O for the word opposite. This is a negative. This is a positive. Opposite sign, positive. Opposite sign, negative. Always positive pertains to the last term is always positive. Always a positive term. Okay. So same, whoops, where was I here? Same signs, opposite signs, and always positive, right? Always positive at the end. So this is the binomial family. I would memorize all of these here. That's how you factor various binomials. And remembering those patterns, obviously, expedites your ability to factor binomials. So let's see if we can factor a couple of binomials here. How about 16t squared minus 49? We want to factor this binomial. Well, you be the judge. What do we got going on here? Is this a difference or sum of squares, difference of squares, sum of cubes, difference of cubes? What do we got here? What do you think? Is 16t squared a perfect cubed or square of a monomial? Is 49 a perfect square or cubed? What do you think?
They're perfect squares.
Yeah, it looks like we got the difference of squares. In fact, 16t squared is the square of the monomial 4t. 49 is a perfect square of 7. So you can clearly see by rewriting it like this, we have the difference between squares. Therefore, the difference between squares always factors into the product of conjugate binomials. So therefore, 16t squared minus 49 will factor into 4t minus 7 times 4t plus 7. Done. That would be the factorization of the difference of those squares. Anybody see here how we're doing this? Product of conjugate binomial. You could have the plus term here and the minus term here. It doesn't matter what order you got these. They just multiply in the product of conjugate binomials. Is this bringing back any memories, ladies and gentlemen? Factoring binomials? These patterns here? Have you seen those before?
Yes.
Yes, yes.
All right. Like I said, it may have been a while. It might be a little rusty, but now's the time to start, maybe getting the rust out, and that's why we got this review section here, R, in our textbook, is to try to bring our minds back to where they need to be. All right, we're going to try to factor this binomial here after thinking about it and a little visual inspection. Hopefully you realize that we got the difference between not cubes, but the difference between perfect squares, because z to the fourth power is not a perfect cube of a factor of z, it's a perfect square of z squared, correct? So, and if you don't believe me, rewrite this in the form of 9z squared minus 1 squared, and you can clearly see that we do have the difference between two squares. Being the case, this has to factor into the product of conjugate binomials. So this will factor into 9z squared minus 1 times 9z squared plus 1. That would be the factorization of 81z to the fourth minus 1. Again, we follow this pattern. The difference of squares factors into the product of conjugate binomials. Okay? Conjugate binomials. Now, something else that we're going to have to always be conscious of is we want to make sure that our polynomials are always completely factored. And so if we look at these remaining factors here, you want to ask yourself, can any of them be further factored down? This 9z squared plus 1 is the sum of squares, and the sum of squares we discovered is always what? Non-factorable. Do you agree? So we cannot further factor down 9z squared plus 1. However, 9z squared minus 1 itself is the difference between perfect squares. This needs to be further factored down because 9z squared is a perfect square of 3z, true? And 1's a perfect square of 1. So this needs to further factor down into 3z minus 1 times 3z plus 1. And of course, the 9z squared plus 1 does not further factor down. We just bring it along. This we say is the complete factorization of 81z to the fourth minus 1. Does that make sense? That's the complete factorization of that. Is that making sense, anyone? Any sense at all?
Yes.
Yes.
This R section is kind of a hassle and it's no fun because it unfortunately might remind us of how much we've forgotten. And that's why it's no fun to go through this R chapter here, or R section. But it's painful at times, knowing that at one time you might have known this stuff, but you got so rusty you forgot it. But you can always get it back, and we just have to try to get it back. Now this is y cubed plus 64. It doesn't look like it's the difference of perfect squares, and it's not the difference of anything because it got a plus sign here. Well, might this be the sum of squares or cubes? What do you think in this case?
Cubes.
Yeah, we're staring at a perfect cube to y here. So maybe it looks like the sum of perfect cubes. 64, is that a perfect cube? You can get on your TI-84 and take the cubed root of 64. In your math menu, if you hit your math button, you'll see a cubed root function not too far down. And that'll afford you, after hitting math, to take the cubed root of 64, and you'll discover that it's 4. So yeah, 64 is a perfect cube of 4. So you can see that we do have the sum of perfect cubes. Being the case, it has to be factored. Uh-oh, but wait, do we remember how? What was that pattern? The sum of perfect cubes. This is how it always factors. See that pattern we need to memorize? And this in general is how we factor the sum of two cubes. I would definitely remember all of these, okay? It's only going to help our cause. So that's how the sum of cubes factors. So this y cubed plus 4 cubed, according to that pattern, is going to factor into y plus 4 times y squared minus 4 times y plus 4 squared at the end. Again, I just follow the pattern. A plus b times a squared minus ab plus b squared. See, I follow the pattern of the sum of cubes. My a is a y, my b is a 4. Okay, let me see how I dropped it in the pattern there. So therefore, we got y plus 4 times y squared minus 4y plus 16. And that is the complete factorization of that sum of cubes. Notice we cannot further factor this trinomial down. There do not exist two factors of 16 that add up to -4. This cannot be further factored down. Hey, if it could be further factored down, don't you think we would have showed you that in the pattern? Don't you think we would have further factored this down or this down? but these are non-factorable. That's why we got to stop right here with this binomial times trinomial. Okay, so all right, so the sum of perfect cubes, that's how that factors there. Okie dokie. And all right, let's try this one. This is an interesting one here. If I got like c squared, c squared, hold on, I'm thinking here, minus 10c plus 25 minus 121. Okay, they want us to try to factor this. Now, temptation would have you adding 25 and negative 121 together. What is 25 minus 121? Can anybody dial it up for me? Just curious. 25 minus 121.
Negative 96.
Okay, now, do there exist two factors of negative 96 that add up to negative 10, the middle coefficient, because it's an easy type of trinomial to factor, correct? Are there two factors of negative 96 that sum up to negative 10? You know, you can get on your calculator and start, you know, going through some trial factors here. And you know what? I honestly can't think of two factors of negative 96 that add up to negative 10. In fact, I don't think there exist any. So initially, if we do this problem this way, by adding these constants together, it doesn't look like there's anything we can do here. It looks like this is non-factorable. Well, ladies and gentlemen, I sit here today to tell you that this can be factored and we need to factor it. We went about it the wrong way. This is not the way to go about it. You don't want to combine these. No, you want to get back and try to see the forest for the trees. Ladies and gentlemen, let's try to concentrate on factoring this trinomial on its own accord first. Can we factor this trinomial here? Notice it's one with a leading coefficient of 1. Do there exist two factors of 25 that add up to negative 10? Two factors of 25?
5 and negative 5.
Yep, two factors of 25 that sum up to negative 10 would be negative 5 and negative 5. So this trinomial can factor into identical binomial factors, namely c minus 5 times c minus 5, and then we got the minus 121. Oh, but wait, c minus 5 times itself is better expressed more compactly as c minus 5 squared minus 121. Ah, now the forest for the trees. Ladies and gentlemen, do you agree I have the difference between what? Perfect squares? Because 121, if you take the square root of 121 in your math menu, there is a, well, no, just above your x squared button on your calculator is a square root function. The square root of 121 is 11. So we do have the difference between squares here. This needs to be factored as the product of conjugate binomials. So therefore, my first term is c minus 5 that's being squared. So this difference between two squares here is going to factor into c minus 5 minus 11 times c minus 5 plus 11. First term minus the second term times first term plus the second term. Everybody see that? A little tricky there. Now we can clean this up. Negative 5 and negative 11 combine to give you minus 16. And these combine to give you 6. So there you go. There we go. Now, if you were to take the time to multiply this all back out, you would get back this polynomial. So this one's a little tricky because you got to kind of just get back and realize that we should factor the trinomial first. And then we realize that we do have the difference of squares in an overall sense. And so we factored it as such. All right, so a little bit of a tricky problem there. Okay, you got that one there? And you know, I notice in your textbook, your author is always throwing you weird problems. Your author doesn't allow you to really get comfortable in your textbook per se. And that's why I provide you with solutions to any additional optional problems that you decide to practice with in your textbook. And I believe Alex is okay and everything, but some of us might have to go into our textbook and maybe do a couple more problems at the end of each section that's covered. And I would recommend doing that, especially to prepare for a quiz or exam. And if you get snagged, you'll have the solutions on Canvas. I'll provide all the solutions for the odds and the even problems. Also, looking at examples in each section that's covered in class would also be very, very, very helpful by studying some of the examples. All right, ladies and gentlemen, we got to try to factor this here, and the worst thing you can do is FOIL this out, and distribute here, and gather all your like terms. That's a lot of unnecessary work here. Sometimes, ladies and gentlemen, by incorporating what is called a U substitution. Has anybody in this class ever heard of a U substitution? Have you ever heard of that before in math? U substitution? U substitutions are used all the time in higher level math, especially the calculus, to try to help us simplify and see the forest for the trees. You know, I'm going to let U be equal to x squared minus 2. It's a harmless U substitution. Let U be equal to x squared minus 2. Now, when we replace, therefore, x squared minus 2 in this polynomial with U, we have U squared minus 3U minus 28. Now, ladies and gentlemen, this looks a lot simpler now. Can we factor this trinomial, this easy type of trinomial in the variable U? Give me a couple factors of negative 28 that add up to negative 3. Couple factors of negative 28 that add up to negative 3. Well, after a little thought, negative 7 and 4 are factors of negative 28 that sum up to negative 3. Therefore, this trinomial factors immediately into the binomials of U minus 7 times U plus 4. Isn't that true? Now we're going to back substitute what we let U be equal to. So we're going to bring back this x squared minus 2 in the end. Replace our U with it. So therefore, the factorization of this messy polynomial is going to be really x squared minus 2 back in for U minus the 7 times x squared minus 2 plus the 4. Everybody see that there? And we can further clean this up now. These combine to give you minus 9. So we have x squared minus 9 times, what does this give you? X squared plus 2. Is there anything else I can do here? Can we further any of these factors down further? Well, difference between squares is x squared minus 9, so it further factors into x plus 3 times x minus 3. This cannot be further factored down. And there you go, ladies and gentlemen, this is the complete factorization of what we started with up here. Do you have to use a U substitution? No, you don't have to, but it sure did what? Take this nasty polynomial and simplify it down into a nice simple what? Trinomial degree in a variable U. It helped us to see clearly how to factor it, correct? In the end, don't forget to bring back what you let U be equal to, though. You got to bring it back in the end, though. Don't forget that. All right, so that's a classic U substitution problem where U substitution can take a real nasty, complex situation and render it virtually trivial so that we can see literally what we're up against, okay? Done all the time in calculus, U substitutions. So U substitutions are used all the time in calculus to help us simplify complex situations down to simple situations. All right, we're fighting the clock as usual, and we are losing the war here. Sometimes, ladies and gentlemen, we might have a negative exponent construct to factor. And they want us to factor this, what looks like a trinomial, albeit we do have negative exponents, so technically it's not a polynomial. But nonetheless, in factoring a common factor out of all three terms here, we want to choose the least exponent. Now, what's the least exponent of negative 7, negative 6, and negative 5? What's the smallest exponent?
Negative 5.
Negative 5 is the smallest exponent?
It's negative 7.
Actually, negative 7 is the smallest of these exponents. Do you agree?
Yeah, because
I know
it's
that seems,
Yeah.
it is. It's,
further away from 0.
yeah, it is. So tell you what, we're going to factor out t to the negative 7th power, which is the greatest common factor, by the way, of all these three terms here, out of all three terms. So when I factor t to the negative 7 power out of the first term, what do I leave behind? What do you multiply t to the negative 7 power by to get back 5t to the negative 7? 5? Now, what do you leave behind when you factor t to the negative 7 out of t to the negative 6 power? or 2t to the negative 6. You know, to help you figure out what you leave behind, you can take this 2t to the negative 6 off to the side of your paper, put it over t to the negative 7, and now reduce this. By reducing it, you'll see what you leave behind. What do we do with exponents when we divide like bases?
You subtract.
You subtract them. So this will be t to the negative 6 subtract the negative 7 power, which is really 2t to the negative 6 minus the negative 7 is negative 6 plus 7, which is really t to the first power, believe it or not. So we leave behind 2t. If you don't believe me, take t to the negative 7, multiply it by 2t to the first, and you will get back 2t to the negative 6th. Finally, when I factor t to the negative 7th out of t to the negative 5, what do I leave behind? Feel free to take the t to the negative 5 off to the side of your paper, put it over to t to the negative 7, and reduce. When we divide like bases, we subtract exponents. So this is going to be t to the negative 5 subtract a negative 7 power, which is really saying t to the negative 5 plus 7, which is really saying t squared. You're going to leave behind t squared. If you take t to the negative 7 times t squared, you will get back t to the negative 5 power. And there we go. A quick check here, ladies and gentlemen. If I was to put this trinomial in kind of like descending order, I don't think it's factorable anyways. 5 times negative 1 is negative 5, and there are no factors of negative 5 that add up to 2, so we're good. This would be the complete factorization. One last little move to get rid of that negative exponent is you might want to flip that t to the negative 7 downstairs and call it t to the 7th power, and that would be our final simplified answer. So anybody see that there, how we factored t to the negative 7th out of all these three terms there? That's something that's often done in calculus. Here's something else that's done. Typical situation that you encounter when you get into calculus, as the toughest part of calculus usually is not the calculus. It's the algebra that's the toughest part of calculus. Any student will tell you that, ladies and gentlemen. So if you're going into calculus, you want to get strong with your algebra. You're going to need algebraic skills to succeed in calculus. Most of the mistakes in calculus are algebraic mistakes. They're not calculus mistakes. All right, so we want to factor this. Do you see any factor that's in common with both these terms here? Well, it looks like both these terms have a 3x plus 1. Do you agree? They're raised to different powers, don't get me wrong, but it looks like they both possess, both this term and this term possess a common factor of 3x plus 1. The question is, how much of this 3x plus 1 can I factor out of both these terms here? Well, it comes down to the least exponent. So what's the smallest exponent of 2/3 and 5/3?
2/3.
So what I can do is I can factor 3x plus 1 to the 2/3 power out of both these terms here. I know this sounds bizarre, but you can do that. So I'm going to factor 3x plus 1 to the 2/3 power out of this first term. And when I do so, what do I leave behind? What would you multiply this 3x plus 1 to the 2/3 power by to give me back 5x times 3x plus 1 to the 2/3 power? What do I leave behind here?
Just 5x.
5x.
That's just a 5x. That's right. Plus, now the tougher question. When I factor 3x plus 1 to the 2/3 out of 3x plus 1 to the 5/3, what do I leave behind? Well, if you're wrestling with that, off to the side of your paper, take the 3x plus 1 to the 5/3, place it over what you're factoring out, the 3x plus 1 to the 2/3, and reduce. How does this reduce? When you divide like bases, you subtract exponents. So what's 5/3 minus 2/3 power?
3/3.
3/3. But another name for 3/3 is to say what? The first power, do you agree? So when you factor 3x plus 1 to the 2/3 power out of 3x plus 1 to the 5/3 power, you're going to leave behind just 3x plus 1 to the first power, or just 3x plus 1. Finally, we would simplify the second factor by combining like terms, and you're looking at 8x plus 1 as being that second factor. Ladies and gentlemen, this is the factorization of this after we factored out the 3x plus 1 to the 2/3 power out of both terms. Did that make any sense how we did that?
So why for the first the 5x, why do we not leave, or why do we not bring the 3x plus 1 over, but for the second one we bring the 3x plus 1 over?
Okay, because we factored 3x plus 1 to 2/3 out of this first term here. Okay, And when you factor this out of the first term, you leave behind, where did I show that there? Well, you factored the 3x plus 1 and the 2/3 out of here. Do you agree? You took this whole factor out of here. You see that there?
Yeah, which left behind the 5x.
5x, that's right. You just leave behind the 5x. When you factor the 3x plus 1 and the 2/3 out of here, you still leave behind the 3x plus 1, albeit to the what? 3/3 or the first power, correct? And
Yeah,
that's- you see it
okay.
now, or?
I guess it just like, I understand like how like it turns into
Because
one,
look,
but I
if you
thought
think about it this way, if you multiply this back in here or distribute this back in, will we not get this back? 3x plus 1 and 2/3 times 5x gives me back my first term, correct?
okay,
Plus, and then 3x plus 1 times to the 2/3 power times 3x plus 1 to the first power. But what's another name for the first power? 3/3
the
power?
3x,
Isn't
yeah.
2/3 plus 3/3 the 5/3 then, correct?
right?
Do you see it now? That this is what you leave behind, because if you were to multiply this back in, you would get this back.
Okay,
Okay, you see that? And that's why 3/3 I called to the first power, and then I just combine like terms here. All right, and that's it.
okay.
All right, golly, I want another classwork, but it just seems like we're out of time here. Okay, so yeah, that's pretty much all I have for today because I'm out of time. It's 4:20, so I gotta let you go. But I will open up a couple of more sections. I already opened up R2 and R3, so I'll open up R4 and R5, correct, and Alex. And so you may want to try to get started on those as soon as possible. Again, keys to success. I did email everybody the keys to success in this class. There's some obvious keys to success. Obviously, show up and view the material that I go over. You also want to open up your textbook, whether it's the ebook or the physical book, and go over some examples in each section. Make sure you study those examples. That's going to help big time to solidify this information. By all means, bare minimum, you got to do Alex, but above and beyond that, if you still need extra practice, do more problems at the end of each of your section. I'll provide you with all the solutions so you can check your results. That's only going to strengthen your understanding of this material if you do extra practice. Now, unfortunately, ladies and gentlemen, because of a contractual hour maximum thing here at Mott Community College, I will not be in the tutorial center, room 2106 in the Gorman building. I'm bummed about that, believe you me. But there will be somebody in that tutorial lab, a capable tutor. I don't know the times and the days of operation of that lab yet. I'm still waiting for my boss to release those times. And as soon as I get them, I will email them to you and also post them on Canvas. So keep that in mind that this center will be open, this tutorial center on the second floor of the Gorman building, the math science building on the main campus, room 2106. It will be opening and in operation. Unfortunately, I will not be putting any time in there, but there will be a competent tutor or tutors in there to help you out with your Math 130. Does that make sense? All right, that's a way to get your extra credit of what, 1%. Do you agree? If you frequent that lab and just have a tutor just kind of sign or initial the days and times you're in there, keep that piece of paper, present it to me at the end of the semester, and I'll tack on an extra 1% onto your overall course average. And another way to get 1% added on to your overall course average is to submit to me at the end of the semester your lecture notes. And I'll tell you exactly what I want you to send as proof of having kept good lecture notes throughout the semester. So stay tuned on that one. I'm not going to have you email me all the pages of your lecture notes. That's just too cumbersome. But I'll tell you exactly what I want as proof, okay? All right, ladies and gentlemen, any other questions? I'll be on the line for a couple minutes. Other than that, if not, have a great day, and hopefully I'll see you on Wednesday.
What will be on the